Hello engineers, I'm Maysam Molana, your instructor in heat transfer online course, and this is the first lesson. What's the heat transfer? Heat transfer is the process of thermal energy transport due to temperature difference. Please keep in your mind, temperature difference is the only reason of heat transfer phenomenon. Temperature difference is the only reason. Temperature difference doesn't work anywhere, anytime between two materials or within a material. Temperature difference doesn't work even in a tiny scales. Anyone who wants to study seriously heat transfer needs to remember always three general rules about heat transfer. The first rule is, for having heat transfer, you need to have delta T, or temperature difference. No any heat transfer without temperature differences occur. The second one is, if you have a temperature difference within a material or between two materials, heat transfer must occur. Heat transfer must occur if there is a temperature difference. And the third rule is, the heat transfer always occurs from a hot source with higher temperature to a cold source with lower temperature. These are three general rules about heat transfer that you need to remember always. We have three heat transfer modes in our studies, in nature, in our routine life, and something like that: conduction, convection, and radiation. You are familiar with these three modes of heat transfer probably, but we need to discuss more about this mode of heat transfer as a lesson of heat transfer. The first mode, or maybe the most famous mode of heat transfer, is conduction. Conduction means conduct some things, conducts heat, conducts energy from a source to the other source. If you have a wall, two walls, a medium, two medium, or something like that, with higher temperature and the other boundary in the lower temperature, you would have conduction heat transfer from a hot source to cold source. T1 should be greater than T2. This mode of heat transfer is related to stationary materials or mediums. It's not important that you have fluid, including gas or liquids or solids. Your medium should be stationary. Velocity should be zero. The second mode of heat transfer is convection. Convection occurs between a solid material and a moving fluid, including gas or liquids, only if there is a temperature difference between surface of solids, surface of your body, and the temperature of moving fluid. For example, in this case, T surface, the temperature of surface is greater than the temperature of upstream moving fluid, and therefore a Q heat, the mode of convection, should be transferred from the body, from the solid surface to the liquid or to the gas fluid generally. And the third mode of heat transfer is radiation. Radiation always occurs from a body with any amount of temperature. Does not important that how many temperature, how many degree you have in your surface. Any surface in any temperature will produce electromagnetic waves, including heat, leading to heating something, carrying energy something to a other surface and something like that. For example, in this case, you have two surfaces in different temperature, and therefore two types of heat transfer with different amounts would be occur. As it's shown, the only common aspects for these three modes is temperature difference. Conduction is the most famous mode of heat transfer and really is a molecular level phenomenon. Is related to molecules activities in gases and fluids, activities including translational, rotational and vibrational motions of molecules. Consider a stationary gas between two walls in different temperature. It's clear that the molecules near to hot wall collide each other, and especially collide to molecules near to cold walls, and this means that there would be a momentum exchange between the molecules, and as you know, the molecule near the hot wall is more lazier than the molecules near the hot wall. And it would be a conduction heat transfer from hot wall to cold wall if and only if T1 would be more greater than T2. Heat conduction in liquids is the same as gases with a small difference. Difference is that the collision between liquids are more stronger than the collision between gases molecules, and these collisions in liquids are more frequent. It means that the conduction in the same condition in liquids should be greater than gases. But everything will change about solids. Atoms in solids are responsible for heat conduction, and today scientists consider lattice waves and lattice vibrational or other type of motions responsible at solids conduction. Consider a wall with boundaries in different temperature. For example, the left boundaries of wall is in T1, and the right boundary of the wall is in T2, and T1 is greater than T2. In this case, we can apply Fourier's law of conduction, that is one of the most famous equations in mechanical and chemical engineering. And as you know, Fourier was a French scientist, important inventions like that, and like Fourier transform in mathematics and something like that. The Fourier's law of conduction says that the conduction heat transfer rho, for example, rho these walls, is equal to minus K times A times the temperature gradient. This term is temperature gradient, and this is one-dimensional example of heat conduction. K is thermal conductivity, A is cross-sectional area of heat conduction that would be calculated through W, the width, and times Z, the height of the wall. In this case, the heat conduction is equal to minus K times A times T2 minus T1 over L as the width of the wall. If you are looking for heat flux, conduction heat flux, you need to divide the amount of heat conduction by the cross-sectional area. This was a brief summary about heat conduction and calculation. We need to show an example to find out how Fourier's law of conduction can be applied to heat conduction problem. Let's take a look at a very simple example on heat conduction. It's a very simple example, but it's required to know how the Fourier laws of conduction works. Consider a wall with different temperatures at the boundaries T1 and T2, and T1 is greater than T2, and we require to determine heat transfer in X direction and heat flux in X direction. Before going to solution, we need to have some assumptions. First of all, the wall is at steady state, means that no changing in anything over time. The second assumption is there is a one-dimensional heat conduction in X direction. It means that no temperature difference in any direction except X. Therefore, no any heat conduction in any direction except X. And we have constant thermal conductivity at the material, means that the thermal conductivity of material is constant anywhere of the material. And if you put in all of known parameters in Fourier laws of conduction, which says that heat flux in X direction is equal to thermal conductivity of material times temperature difference over the length of the material, gives that heat flux in X direction is equal to 2833 watts per meter squared. And we know that heat conduction in X direction is equal to heat flux in X direction times the surface area, and the surface area is equal to length over length times the width of the wall. And if you plug in again the known parameters into this equation, gives that the heat conduction in X direction is equal to 700 watts. Let's take a look at heat convection. When a fluid is moving over a plate, and if there is a difference between the temperature of fluid and the temperature of solid plate, a convection mode of heat transfer definitely will occur. You can see in this picture that we would have had hydrodynamic or velocity boundary layer because of the velocity change here, because of no slip condition at the surface of plate. Similarly, we have a thermal boundary layer here if a temperature difference exists. But if you want to calculate the heat transfer here, you need to use Newton's law of cooling, which says that the heat transfer is equals to heat transfer coefficient times the surface area times the temperature difference. And if the temperature of heat conduction, the temperature of the plate is greater than the temperature of the fluid, heat flux will occur from the plate to the fluid. But when you are talking about convection, really you are talking about a collective effect of two energy transport mechanisms. First of all, diffusion, which is a macroscopic phenomenon, means that the energy transported via the random motion of molecules of moving fluid. And the other energy transport mechanism is bulk motion or advection. That is a macroscopic phenomenon. So, if you want to talk about convection, really you need to know that you are talking about the collective effect of two energy transport mechanism. Simply, we can categorize convection into main classes of convection. First of all is forced convection, which occurred by a pump, fan, or atmospheric wind, or something like that, and the natural or free convection, which is due to the temperature difference, leads to density difference into different location, which consequently leads to buoyancy effect, and natural convection occurs. The important thing that you need to know here is the behavior or the value range of heat transfer coefficient as a function of the mode of convection. For example, in natural convection, the value range of heat transfer coefficient is narrow for gases and will be greater for liquids. And for forced convection, this value range will be much greater, and for boiling and condensation we would have a much greater values of heat transfer coefficient. Means that boiling or condensation gives greater heat transfer coefficient than forced convection, which forced convection will gives a heat transfer coefficient greater than natural convection. And then another important finding from this table is that generally the heat transfer coefficient for liquids is greater than heat transfer coefficient of gases. Now I want to talk about heat radiation, which typically occurred by electromagnetic waves. As you probably know, electronic magnetic waves don't need to any material for propagating, and they will propagate in the presence of material or in the vacuum condition. And this type of waves emit from all type of materials, including gas, solids, and liquids. To calculate the heat transfer mode of the radiation mode of heat transfer, we need to define some different parameters. I wrote all of them here. First of all, we need to know that the emissive power of a surface or of a material is equal to Stefan Boltzmann constant and emissivity times the temperature of surface powered by 4. This is the Stefan Boltzmann law, which gives you the emissive power of a material or of a surface. But this power is limited by an upper limit, an upper constraint, which is EB is equal to Stefan Boltzmann constant times the temperature of surface powered by 4. Means that here the emissivity is equal to 1, which means that we have a black body. Black body is an ideal radiator and gives the higher level of heat transfer, radiation heat transfer at the given condition. Now we need to know that emissivity change from 0 to 1, which 1 is related to black body, and in heat radiation scope, generally temperature is considered as absolute temperature in Kelvin. And if you want to calculate the heat transfer by heat conduction, heat radiation, you need to use this equation, but this equation is more general than the other, means that heat radiation is equal to Stefan Boltzmann constant times emissivity, which is change between 0 to 1, times the difference of temperature of surface and the temperature of surrounding or temperature of the other surface. Okay, now let's solve an example to find how convection and radiation modes of heat transfer will be considered and calculated at the same time. Consider a pipe in a larger environment or larger surroundings. This pipe's geometry is known except the length of the pipe, and has a surface property or emissivity is equal to 0.8, and the temperature of the surface is 200 degrees C, and we have a moving air at ambient temperature, which is 25 degrees C, and we know that these pipes definitely will emit electromagnetic waves because its temperature is not absolute zero, and any material which its temperature is greater than absolute zero will definitely emit some electromagnetic waves. And we need to find emissive power of the pipe and heat loss per length for the pipe. Before going to solve this problem, we need to consider some assumption. First of all, our pipe is at steady state, which means nothing changes over time, and we have a large enclosure or large environment or surrounding over the pipe. First of all, to calculate the emissive power of the pipe, we need to use Stephen Boltzmann law. If you plug in all of known parameters here, you can find that emissive power is equal to 2270 watts per meter squared. But please remember that T temperature here is 200 degrees C and should be plus by 217.3 because it should be absolute temperature in Kelvin. After that, to find the heat loss of the pipe, we should consider an energy balance. Comes from first law of thermodynamics. As you probably remember, the collective heat loss of the pipe should be equal to the heat convection from the pipe to the environment and the radiation modes of heat transfer from the pipe, and the surface area of the pipe is equal to the perimeter of the pipe times L, which is equal to pi d times L. And if you plug in the equation for convection modes of heat transfer, which is Newton's law of cooling and Stephen Boltzmann and the equation for heat transfer, radiation heat transfer here, we have two L here, and if you plug in again all of known parameter here, we can find that Q over L, which is heat loss per length of the pipe, is equal to 998 watts per meter. In most of personal experience or industrial applications of heat transfer, you have 2 or 3 modes of heat transfer at the same time. We just finished the first lesson of heat transfer online course, and we reviewed the different modes of heat transfer, including conduction, convection, and radiation, and we have solved 2 examples of heat transfer, 2 very simple examples. And at the second lesson, we will focus on conduction more deeply and define the equation, first of all derive the equation, define different and diverse parameters, and we will solve some more difficult problems.